Okay, so working through question 1 on this set of questions I gave you. So this one's obviously about gravitational fields. You can see the lines in figure 1 show the shape of the gravitational field around two stars G and H. Essentially, obviously, we're going to be looking at these and thinking about how strong the gravitational fields must be by this demonstration of the field lines. Okay, so compare with reference to figure 1, so it's important, right? You've got to use what's in the figure 1. I mean, that's pretty obvious for this one, but make sure if that's ever in a question, you are using the data from that and not from anything else given to you in the question. Okay, compare with reference to figure 1 the masses of G and H. So what we're going to look at here is there's a couple of things we can look at. Okay, there's a few things that tell us this. The first thing is going to be the density of the field lines. Okay, so where are the density of the field lines greatest? Okay, that's going to tell us where the field strength is the greatest. Okay, and the field strength will be the greatest where the mass of that object is the greatest, right? Because then the other thing in that is going to be related to the gravitational constant. So where the field lines are densest is going to tell us where the mass is the greatest. And here we can see the distance as we get close to G between these field lines is much smaller than the distance between the field lines of H at the same point, right? So that's our first telltale sign that G has a greater mass than H. So you can say that's because of the density of the field lines near to the masses, or you could point out that the null point, the point essentially where the object would feel no force or no resultant force, is going to be closer to H. Okay, and if you essentially think about the idea, if it's close to H and it's going to feel the same amount of force it feels from both masses, then it must be that G has a greater mass in order to account for that extra distance, okay, to result in the same force. So those are two things. We're going to talk about the field density, and we're going to talk about the null position in relation to the two objects. X and Y are points in the field. Annotate figure 1 to show the direction of the field at X and the field at Y. So a few of you, a couple of people actually missed this. So make sure when you're going through papers, you're looking for these, right? These are telling you where you need to answer questions, right? This is a sort of classic basic exam technique, but you need to make sure you are remembering these exam basics. Okay, so X and Y are 2 points in the field. And we're going to show the direction, show the field direction at X and the field direction at Y. So by that it means essentially we're going to show the direction in which the field is acting, or the force the object would feel, the non-contact force the object would feel because of its point in that field. So that's always going to be signaled by the field lines, right? They're always going to act, the force is always going to act along the field lines. And then you remember from our study of gravity that gravity is only ever attractive, right? It's only ever going to act towards the mass. So what we can say is in both these examples here, we can say, well, this one is going to be acting along the line here, and this one is going to be acting along the line here. Okay, and then you've got a spherical asteroid P, has a mass of 2.0 times 10 to the 20 kilograms. The gravitational field strength at its surface is 0.4 newtons per kilogram. Okay, and calculate the radius of P. Well, what we're going to think about here is obviously we know our initial force equation was G, mass of the object generating the field, mass of the object in the field over r squared. Okay, we know that we can divide out the mass of the object in the field to get the gravitational field strength of that field, right? Because force over the mass of the object in the field will give us that. So G is going to be equal to Gm over r squared. Okay, and then what we're trying to find here is the radius of the object, right? So we're going to look at, well, this is the gravitational field strength at its surface. Okay, so this here would be the gravitational field strength at the radius, where this r would essentially equate to the radius of the object. Okay, so what we're going to do is we're going to rearrange for r, which means r would be equal to, we're going to divide G out, and then we're going to say root Gm over the field strength. Okay, and then if we plug in our numbers, we get r is equal to 6.63 times 10 to the negative 34. Sorry, 11, thinking about Planck's constant, times 2.0 times 10 to the 20 over 0.4 newtons per kilogram, which is this here. And that should give us an answer of, so we're doing the maths, what do we get? We get 1.8 times 10 to the 5. Okay, meters. 6, we're talking about the radius. Okay. So then what we're going to do is go on to the next question here. So sketch on figure 2 the variation of gravitational field strength G with distance r. The distance r is measured from the center of P. Okay, so we've got our change in gravitational field strength essentially as we move out from the object. We're going to treat the object as a point force here. Okay, so we know that at r, okay, r is the surface, right? So that's where we're going to start here. We know that r is the surface, so we don't need to worry about that linear change within the object because we're starting at r, which is our surface. All we're thinking about here is the inverse square law. So any particular change in force is going to be equal to or proportional to 1 over the square of the distance. So if we say here we've gone 2r, which is double distance, square of that obviously is 4, so it's going to be 1/4 the force. So we're going to put a mark at 0.1. 3r would be 1/9 of the force, so we're going to put a mark at 0.044. Okay, so essentially what the mark scheme will allow you here is a clear marking at the point between those two, 3r, and then obviously we're going to draw our line in. Okay, curved line into there. Right, E. Explain what is represented by the area under the graph between R and 2R, sorry, on figure 2. So we're looking here, what's the area under this graph? Okay, a bit of a poorly drawn line. Obviously do that a bit better. My pink one came and screwed there. When you're doing that in exams, and obviously use pencil so you can edit it if you do have a slip up like that. So R to 2R, so what is the area under this graph representing? Well, we know that the area under a graph is obviously the x-axis multiplied by the y-axis. So we're going to say, well, what is represented by G multiplied by R? And for that, we're going to look at, well, what actually equation-wise is kind of do we get from that? So if we look at our equation for G again, G is going to be equal to Gm over R squared. Okay, we're going to multiply that by R, which means obviously we're multiplying out one of these. So we get Gm over R. Some of you should already hopefully recognise what we're going to get, which is going to be V, our potential, right? The important thing then is you go on to say that these two multiplied together will give you gravitational potential, and that therefore between R and 2R, the area under the graph will be representing the change in gravitational potential from R to 2R. Right, so asteroid P approaches the two stars G and H. Figure 3 shows one position of P close to H. Okay, so here we go, we got this here. So basically we've got this thing orbiting around H and also being influenced by the gravitational force from G. So G is 6.38 times 10 to the 12 newtons. The mass of H is 3 times 10 to the 25 kilograms. Gives us the mass, and distance HP is 1.5 times 10 to the 11. Okay, so the way we're going to think about this here is what we essentially have here is we have a sort of forces diagram, right? We have, if we can work out what some of these forces are, we can work out what the forces acting in all three of these lines is. So therefore what we're going to do is we're going to think about this in terms of Pythagoras theorem, and we can say, well, this one here, the force on P from G, so this side here is 6.38 times 10 to the 12 newtons. So then we just need to work out one of these others, and obviously we can work out the last one. So the mass of H is 3 times 10 to the 25. The mass of P is 2 times 10 to the 20. So we got the mass of both of these. Okay, so we'll be able to work out this force using Gmm over R squared, because we have distance HP as well. Okay, so therefore that is going to be equal to 6.67 times 10 to the negative 11 times 3.0 times 10 to 25, times 2 times 10 to the 20, and we're going to divide that by distance between them squared, 1.5 times 10 to the 11 squared. Okay, and that's going to give us a force acting here of 1.8 times 10 to the 13. Okay, And then if that gives us 1.8 times 10 to the 13, we can then plug that in. Okay, so if we say this now is 1.8 times 10 to the 13, that means that this final force here, the sort of hypotenuse of this triangle, is going to obviously be a squared plus b squared equals c squared. So therefore, for our total, we're going to say, well, the sort of total force, okay, acting along here is going to be square root of 1.8 times 10 to the 13 squared plus 6.4 times 10 to the 12 squared. Okay, and then calculate this already. So that's going to give us a total of 1.9 times 10 to the 13. And then what we're going to say is, well, the question is, what's the magnitude of the acceleration of P? Okay, so what's the magnitude of the acceleration of P? We're going to take that total force there. That's essentially what we've worked out, right? The two forces acting on it are this one and this one. So the sort of resolved force total acting on it is 1.9 times 10 to the 13 along this line here, and therefore we can say, well, obviously acceleration is force divided by mass, which is going to be 1.9 times 10 to the 13 divided by 2.0 times 10 to the 20, our mass here of P. Okay, and that's going to give us an acceleration of about 9.4 times 10 to the negative 8 meters per second squared. Okay, and then last one of the first question, explain why P cannot have a circular orbit at H. Okay, around H, sorry. So if we look at this, it can't possibly be a circular orbit, because in order for a circular orbit to take place, there's a few sort of rules that are going to need to be followed, right? Firstly, it's going to have to move along an equipotential, so there can't be anything essentially performing, doing work on the object. And secondly, if we're going to follow a circular orbit in that same vein, all of the force would have to be a centripetal force accelerating it only in terms of changing its direction and not its velocity, therefore not doing work on it. Now G is impacting that and changing that. Now one of the key things about this is, I will point out to you, you do have to explain that, right? So G, the resultant force is not centripetal and continual directed towards H. You can just say directed towards H. You didn't have to say centripetal for this question, but please get used to using that obviously term for anything that's acting towards the center of a circular orbit and acting perpendicular to the object. And then a circular orbit does not follow gravitational equipotential. So you could also say that it doesn't follow gravitational equipotential. It would be impacted by G. You can't just put there G would change it or something like that. Okay, you need to explain your thinking in terms of what is G stopping that's causing it to not have the circular orbit.